Okay, so this is the start of the nodal analysis examples lecture. So we're going to work 3 or 4 examples here. We're going to start with this problem, so I'll give you a second to write it down. If I were you, I would try to pause the video and see how far you can get working it yourself, and then come back and watch me work it. This one has something that's a little different in it, so so it might be a little more challenging, but I think it would be good for you to at least give it a try. Okay, so we're going to start by identifying the nodes with 3 or more connections. There are several. There's one here, there's one here, there's one here, and there's one here. Okay, so we have to pick one of these to be the reference node, and we can pick any one of them to be the reference node. It does not matter which one, but there is one that makes the math for this a little less tedious. So when I say less tedious, it means we have fewer equations to solve. And so that's if I choose this node to be the reference node. Okay, so then I'm going to label these other nodes with node voltage variables. I'm going to call this one V1, this one V2, and this one V3. Okay, so why did I choose this one to be the reference node? So it's because I've got this voltage source here, and it is isolated between 2 nodes, meaning there's no resistor, no other element between the source itself and the 2 nodes on either side. Okay, and so what this allows us to do is it allows us to solve for one of the node voltage variables immediately if we choose one of them to be the reference node. Since we've chosen ground to be on this side of the voltage source, what does that mean for the voltage V1? It means that V1 is equal to 5 volts. Okay, we know that before we even get started. There, 5 volts, a little bit better. Okay, so again, plus V1 here that we've labeled V1 minus the reference node ground has to equal 5 volts. So V1 has to be 5. Okay, now if you had chosen this to be the reference node instead, and this to be V1 instead, then what would V1 be? It would be minus 5, because the polarity would have shifted, right? We'd have plus 0 minus V1 is equal to 5. Okay, so what about this makes the circuit analysis less tedious from a math point of view? Well, once we know what the node voltage is, okay, we don't have to worry about writing an equation for that node voltage in order to solve for the other node voltage variables in the circuit. Okay, we may need to write that node voltage equation later, but it'll be for something very specific. Okay, but in order to find V2 and V3, we don't need that node 1 equation because we know what it is. It's 5. All right, so let's write the rest of our nodal equations. So the node 2 equation, I'm going to stop drawing in those current arrows. So, but we're going to solve for the current flowing out of the node. So the current flowing down is going to be V2 minus V1 over 10. Oh, let's take one step back here. I'm going to erase this, and we're going to take a giant step back. Okay, so now we know that V1 is 5. Let's look at this voltage Vx, and I'm actually going to erase it and do a different color so it stands out a little bit more. That's why I didn't see it. Let's do green. All right, so that voltage Vx there. So Vx is the voltage that we're going to solve for here. And so it makes sense to write down what the expression is that we need to solve for that voltage. Okay, and that equation is just going to be an electrical body equation. So plus V2 minus V1 has to equal Vx. So we'll write that down here, that Vx is equal to V2 minus V1. Okay, and I'm going to call this little section things that we know. We know these things before we even get started with writing nodal analysis and the nodal equations. We know what these two things. Okay, we know what we're trying to solve for, and we know what V1 is. Okay, now let's go to the node 2 equation. Okay, so as we go to the node 2 equation, we're going to deal with this Vx here. And what I want you to do is I want you to ignore it for the technique. We have written down what Vx is. Okay, so it's even better to just go ahead and erase this off of your paper, okay, until you have to go back to it. We've written it down here, so we know what Vx is. So now we just need node 2. All right, so our node 2 equation. So we're going to solve for the current flowing down, the current flowing to the left, and the current flowing up. Okay, so the current flowing down is going to be V2 minus V1 over 10. The current flowing up is opposite the current source, so we're going to add minus 8. We've got to change the sign on that current source. Plus the current flowing to the left is going to be V2 minus 0 over 4, and you do not have to include those minus zeros. Let me move this over just a little bit so we're not so packed into the edge there. Okay, so that's our node 3 equation. Okay, node 2 equation. Now our node 3 equation. All right, we're going to again solve for the currents leaving the node. Okay, so notice the current flowing to the right is this kind of big. We have to go all the way down here to V1 to get our voltage drop. So the current flowing to the right is going to be V3 minus V1 over 5, plus the current flowing down is 8, plus the current flowing to the left is V3 minus 0 over 1. And I'll stop putting in those minus zeros as we move through these examples. All right, so we have two equations here, two unknowns, because we know that V1 is 5. Okay, again, just to remind you, as we're looking at the voltages across the currents through the resistors, when we look at those voltage drops, it's the voltage, the node voltage for the node we're handling, minus the voltage on the other side divided by the resistance. Okay, so we're going to solve these two equations, these two unknowns, and when you do that, you'll get that V2 is equal to 24.29 volts, and V3 is equal to minus 5.83 volts. Okay, so those are our two node voltage variables. And so now that we have those, we can solve for Vx. So Vx again is V2 minus V1, or Vx is equal to 19.29 volts. So that's Vx. So now we have to go back and find the power delivered by the 5-volt source. And in order to solve for the power associated with the 5-volt source, we need to know what this current is. And right now we don't have any equation, we don't have any information in this circuit right now that tells us exactly what that current is. And so this is one of those situations where we didn't need the node 1 equation to find node 2, node 3 node voltages and find Vx, but we are going to use it to find the current through that 5-volt source. So now we're going to write that node 1 equation. And I'm going to grab the circuit here and pull it down so we can see it. Well, yeah, that's it. Okay, so let me just fix this one that's missing. All right, so we're going to write our node 1 equation. So we are going to sum the currents leaving the node. Okay, so that's going to be the current flowing to the right. So node 1 is going to be V1 minus V3 over 5. The current flowing up is going to be V1 minus V2 over 10. And the current flowing to the left, that's this current flowing in this direction. So when we look here, what do we see? Remember the hierarchy for writing down currents. Is there a current source here? No. Is there a resistor here? No again. So we have one other option, and that is to label a current variable and give it a direction. Those are the only three ways we can write down currents. We can't do the first, we can't do the second. So our third option is the only option that we have. And so I'm going to label a current, I'm going to label this current, that direction, and call it IS. You could call this any current name you want, IB, I-47, whatever you want to call it, and you could give it either this direction or the opposite direction. It does not matter. I chose this direction because the problem asked us to solve for power delivered by the source, and so IS will give me power delivered. So now we go back. We have to write the current flowing in this direction. So that is that current. IS flows opposite, so we will add a minus IS, and that sums to 0. All right. So we'll substitute in V1, V2, and V3. We have those, okay? And we can solve for IS. And when we do that, we'll get that IS is equal to 0.237 amps. So now we're going to find the power delivered by the 5-volt source. Let's call that 5 volts. So that's equal to V, the value of the source, times I, that current IS that we just solved for. And this is going to be 1.18 watts. And this is delivered because of the way we labeled and chose the reference for IS. We solved for power delivered. We don't have to worry about changing signs, changing directions. Okay? All right, let's do another example. Okay, so we haven't seen dependent sources in a while, but we're going to have one here. I'm going to move this circuit over so I've got a little more room on each side. Okay, so this is a voltage-controlled current source that has a value of 3Vx. This is a 3 ohm resistor. This is a 2 ohm resistor. This is a 1 ohm resistor. This is a 3 amp source, a 10 volt source, and this is the voltage Vx that controls this 3Vx source. Okay, and we are going to solve for the voltage Vx. So we're going to find Vx and the power absorbed by the 2 ohm resistor. Okay, I would encourage you as you work these problems to find the power delivered and absorbed by every element. You will have to do that undoubtedly on the first exam. So I would continue to practice that. I'm happy to go over your work with you. I'm not going to do it every time, but I would certainly encourage you to take a look at some of these. Okay, so identify nodes. We've got a node down here at the bottom where everything's connected. We have a node here, and we have a node here. I'm going to ground this bottom node here. I'm going to call this V1 and that V2. Okay, so in general, I like to start off by writing down things that I know. Whenever you have a dependent source in your circuit, you should write at least what the controlling element is in terms of the variables that you're dealing with. So we have a dependent source in the circuit, this 3Vx, this voltage controlled current source. So the current here delivered or provided, not say delivered, provided by the source is a function of the resistance 1, the voltage drop across that resistance Vx. Okay, and so what is Vx in terms of the node voltage variables? Vx is equal to plus 0 minus V1. Okay, so we know that. So let's go on and write the rest of our equations. So we'll start with node 1. The current flowing to the left is minus 3, opposite the source. Remember, we don't worry about Vx here anymore. We've written down what the relationship is. We're really only interested now in the node voltage and the 1 ohm resistor. So I encourage you to leave Vx alone after this. Okay, so plus the current flowing down, which is going to be Vx minus 0, or excuse me, I just said it, V1 minus 0, V1 minus 0 over 1, plus the current flowing to the right. Now this is a little different because now we have this voltage source here and ground isn't on one side. So this is going to take a little bit of work to figure out, okay? So I'm going to put, and I'll put a green node in here, a green node there. And so what we're trying to find out here, again, we're solving for the current flowing in this direction. So we need the voltage drop with that polarity across that resistor. At the minus terminal, we know what it is. It's minus 2. So we need to know what that node voltage is in order to figure out what that voltage is, that voltage drop is. Okay, so this voltage, I'm going to call it V, I'm going to call it Vx again. No, not Vx, because we've just used Vx. We'll call it VA. Okay, so what is VA equal to? So we have VA minus V1 has to equal 10, right? So VA is equal to V1 plus 10. And I wrote this wrong. Let's try this again. VA plus VA minus V1 has to equal 10. So VA is equal to 10 plus V1. Okay, so just electrical body stuff. VA minus V1 is 10. VA is equal to V1 plus 10. So now when we look at the current flowing in this direction, the voltage drop is going to be VA minus V2. So this voltage drop is going to be V1 plus 10 minus V2 over 2. And this is going to sum to 0. And once again, I misjudged the amount of space I would need. Let's just put this down there. Okay, our node 2 equation. Let's look at the current flowing to the right first. So again, we're summing the currents, leaving this node. Okay, so the current flowing to the left is 3Vx. Okay, remember it's the current, and the current is 3 times Vx, plus the current flowing down, which is going to be V2 minus 0 over 3, plus the current flowing to the right now. We want the current flowing in this direction. So it's going to be V2 minus VA over 2, or V2 minus 10 minus V1 all over 2 is equal to 0. Okay, so we have 1, 2, 3 equations and 3 unknowns, V1, V2, and Vx. And so we can solve this, okay? Certainly we're going to put V1 in here for Vx, and then we have 2 equations, 2 unknowns. And so we'll solve these. We'll have V1 is equal to minus 1.67 volts, we'll have V2 is equal to minus 1 volt, and then Vx is equal to plus 1.67 volts. So there are our node voltage equations, and there is the voltage we were asked to solve for. Okay, so now we need to look at the power associated with the 2 ohm resistor. Okay, so again, I like to use V squared over R when I have when I'm solving for power with resistors using nodal analysis. All right, but it does not matter. Okay, so here I'm going to use I squared times R just to show you that it doesn't matter which way we go. So, what is the current through the 2 ohm resistor? Well, it is sitting in our nodal equation, right? We solve for the current flowing in one direction through the resistor here, and in the other direction flowing through the resistor here. Does it matter which version of that current we use? The answer is no, because we are squaring it. So it doesn't matter which one we use. We'll get the same answer regardless. So I'm going to use that this power is equal to V1 plus 10 minus V2 all over 2. We'll square that, and then we'll multiply it by that 2 ohm resistor there. And that will give us our power. And when we plug everything in here and solve, we'll get that this is equal to 43.55 watts. And this is absorbed because resistors can only absorb power. Okay, so we worked this problem where we had a little bit trickier to get the voltage drop across the resistor in this branch here with this voltage source, and we also had a dependent source. It doesn't change how we do things. We just have to account for them when we write the equations and then continue. All right, one more example, and then we will be moving on to a new technique. All right, so all right, so okay, so we have a 2 amp source here. We have a 5 ohm resistor here. We have this 2 VB dependent source. So this is a voltage controlled current source. And then here we have 0.5 IB. We have a current controlled voltage source. We have a 1 ohm resistor here and an 8 volt source here and a 4 ohm resistor here. The voltage that controls this dependent source 2 VB is this voltage here. And actually, I'm going to draw that in a different color because that starts to get a little monotone. So this is VB, and then the current IB that controls that current controlled voltage source is here. This is IB. Okay, so let's solve this using nodal analysis. We are going to find IB and VB. Yeah, we're just going to solve for those two. Okay, again, I encourage you to solve for power delivered and absorbed for each one of these circuits all the way through. It's great practice and it really builds confidence, but we're just going to stop with IB and VB. Okay, so let's label some nodes here. So There's a node here with 3 or more connections. There's a node here with 3 or more connections. There's a node here with 3 or more connections. And there's a node here with 3 or more connections. So I'm going to ground this bottom node, okay, for a good reason, because this 8-volt source is isolated between this node here, which I've labeled as V1, and the ground node. So this means, just like the example we worked before, that V1 is equal to 8. And then I've labeled the other 2 nodes here. Okay, so V1, so we're going to start by things that we know. We know that V1 is equal to 8 volts, just by the way we have labeled the reference node and the other voltages in for the node voltages. So since we have 2 dependent sources in the circuit, we should determine what the controlling elements are in terms of the node voltage variables, VB and IB. So VB, what is VB equal to? VB is the voltage drop across the 4 ohm resistor. So we have plus 0 minus V2 has to equal VB by electrical bodies. So VB is equal to minus V2. IB is just the current flowing in this direction, so we can write down what its value is in terms of the node voltage variables. It's going to be V3 minus V2 over 5. Passive sign convention holding, we want to solve for the voltage with that polarity, so the current's flowing from plus to minus. So plus V3 minus V2 over 5. Okay, so we know what V1, this node voltage, is, so we do not need an equation here. And we won't need an equation until or unless we're going to solve for the power associated with the 8-volt source. We're not going to do this here. I strongly encourage you to do so. But we do not need a node 1 equation to write the, to solve for the other 2 node voltage variables. So what I'm going to do is I'm going to put node 1, don't need right now, okay? So the reason why I do this is because I find that sometimes students are just inclined to write down that equation here. And if something goes wrong and you've used it to solve for the other 2 node voltage variables, then everything is going to be wrong after that. So if you don't need it, don't write it down until you absolutely need it. Okay, so let's go with node 2. So our node 2 equation, again, we're solving the currents leaving the node. Okay, so the current flowing to the right is going to be, forget about IB, we're interested in the technique. We want the current flowing to the right. So that is V2 minus V3 over 5. Plus the current flowing down, forget about VB, remember the technique, it's going to be V2 minus 0 over 4. Plus the current flowing to the left, okay, it's going to be V2 plus 0.5 IB minus V1 over 1 is equal to 0. Okay? Our node 3 equation, again, summing the currents leaving the node. Okay? I'm going to pull this down just a little bit. So the current flowing up here is going to be 2 VB. It's going, the current source is going in the same direction we want to express the current. So 2 VB. The current flowing to the left, forget about IB, although this is IB in this case, plus V3 minus V2 over 5, plus the current flowing down opposite the current source, so minus 2 is equal to 0. Okay, so we have, if we look at these 2 nodal equations, we have 2 equations and we have 1, 2, 3, 4, 5 unknowns. But we pull up and we've got 1, 2, 3 more relationships. So now we've evened out. We have 5 equations and we have 5 unknowns. And we will simplify. So I'm going to do that for you here just because these are kind of complicated. So we know that V1 is 5. We know that IB here is V3 minus V2 over 5. Okay, we know that VB is minus V2. All right, so we're just going to plug all of those in and simplify these equations down. And when we do that, we'll get that node 2 will simplify to V2 times 1.35 plus V3 times minus 0.1 is equal to 8. And then node 3 will simplify to V2 times minus 2.2 plus V3 times 0.2 is equal to 2. All right, so two equations, two unknowns. We'll solve for V2 and V3. And when we do that, we'll get that V2 is equal to 36 volts and V3 is equal to 406 volts. When we take V1, V2, and V3 and substitute it into our equations here, okay, we can solve for VB and IB. We'll get VB is equal to minus 36 volts minus V2, and IB is equal to 74 amps. Okay, so let's talk a little bit about numbers here. When I come up with circuits for you guys to solve, I don't think very hard about, am I giving you realistic currents and voltages? Certainly, we're not going to build a tabletop circuit that has 74 amps of current in it. So don't look at voltages and currents values alone and say, well, that's way too high. She would never give us anything like this. I must have the wrong answer. Okay, I try to on circuit problems on exams to keep those values reasonable. Sometimes I don't always make that happen. So there's no reason to assume that just because this is a really high current that somehow the value is wrong. But I encourage you to solve for the power delivered by the sources and absorbed by the resistors. I will probably work this problem and do power delivered and absorbed. I'm going to try to have one live session next week, and I'll do that just so you can see it. But I encourage you to do it. I'm going to try to have a live session next week. Okay, this is nodal analysis. The rules never change. You can take any circuit, any of the brute force circuits that we've worked, any circuit that is in a problem set that has resistors and voltage and current sources in it. I may have said solve it using superposition or solve it using a different technique. There's no reason why you can't take that circuit and solve it using nodal analysis and get the same answer. So practice, practice, practice. And please practice the math. I cannot tell you to say it enough that if you wait to the exam time and say, well, I'll just do the math then, you will have a time management problem on the exam. You've got to practice this math. Dealing with fractions is always a little bit more challenging. So please, please practice the math. Don't just assume that it's easy. It is easy. It's trivial math. It's math that you can do. But if you don't practice and you don't get some muscle memory down, you will find yourself having a time management problem. All right, so that's all for nodal analysis.